So question 1. We have a system, 2 degrees of freedom. Very simple. Should be no problem. Here we've got K. Here we've got 2m. We've got K here, M here, and K. And we've got 2 directions. X1 and X2. So I'm just reproducing what's in the diagram in your book. And the question says, find the equations of motion in matrix form, find the radiant natural frequencies and the Hertz natural frequencies, and go on to find the mode shapes. I've not given any values for K and M, we just have to work it out in terms of K and M. So there's our system. Equation of motion, E, O, M. It's quite straightforward. Our mass matrix, we've got the 2 masses in the diagonal, 2m and m. Everything else is 0. That's multiplied by acceleration, x1 double dot, x2 double dot. There's no damping, so we don't need to worry about that. We have a stiffness matrix. Now the first box, this one here, we take the first mass and we add up the springs connecting this mass to either ground or to another mass. So we end up with k plus k. So we've got 2k. The second diagonal, you take this mass and you add up the springs connecting it to ground or to another mass. K plus k, 2k. So that's the other diagonal. For the off diagonals, you take the first mass and you add up the springs connecting it to another mass, k, but you take the minus that sum, so it's minus k for the off diagonals. And the same thing, second mass, springs connecting it to another mass is just 1, k, okay, but it's the minus the sum, so it's minus k. So there's our mass, there's our stiffness matrix, x1, x2 equal, there's no forces being added, so that equals 0. Does everybody agree that that's quicker than doing mass times acceleration equals the sum of all the forces, yeah? It's much quicker just to jump straight to that matrix form. And if you multiplied it out, you'd get the 2 equations of motion that you would get with a mass times acceleration. Newton's second law. So that's the equation of motion, which is what we were asked to find first off. Now to find the natural frequencies, we apply the substitution that xi is big Xi cosine of omega t plus phi. Okay, and if we take the second derivative of that, xi double dot equals minus omega squared, big Xi cosine omega t plus phi. And so if we plug that in, we end up with minus omega squared 2m 0 0 m I've already dropped the cosine term because we know that cancels, so that's not appearing in here. And so we end up with, for the mechanical impedance matrix, we've got 2m omega squared, that's a minus sign there, plus 2k minus k and minus 2m omega squared plus k plus 2k. Obviously we've got a minus 2m here and we've got a minus m down here. The 2 there is wrong. Okay, so cross that out. So I shall rewrite this box. So some natural frequencies. So, to find the natural frequencies, we need to find the determinant of the mechanical impedance matrix, MIM, and that must equal 0. And so, we can do that. So, if we take, we've got 2k minus 2m omega squared, which is this term, multiplied by this term, 2k minus m omega squared. Those two terms minus, then these two terms that multiply together, minus k equals 0. So here we've got 2k times by 2k, so that's 4k squared. Okay, here we've got 2k times by minus m omega squared, so that's minus 2k m omega squared. Then we've got minus 2m omega squared times by 2k, so that's minus 4k m omega squared. And then minus 2m omega squared times by minus m omega squared, so that's plus 2m squared omega to the power of 4. And then we've got minus k times minus k, well minus k times minus k is k squared. Obviously that's going to be a minus k squared there, equals 0. So if we rearrange this to solve, to put it in sort of terms of quadratics, we'll put the omega to the power 4 term first. Then here we've got minus 2km times by omega squared and minus 4km times omega squared. And so we have minus 6km omega squared. And then here we've got 4k minus k, so that's plus 3k squared equals 0. Let's apply the quadratic formula. So omega 1, 2 squared, okay, because obviously it's in terms of omega 4, minus b, so that's 6km, plus or minus the square root of b squared, so that's going to be 36k squared m squared, minus 4 times by a, 2m squared, times by c, 3k squared, divided by 2a, so that's 4m squared. Now under the square root, 4 times 2 is 8, times by 3 is 24, 36 minus 24 is 12, so we end up with root 12 m squared k squared. So I'll have this line in here, 6km plus or minus the square root of 12 m squared k squared divided by 4m squared so the square root of 12, obviously that's square root of 4 times 3. 4 square rooted is 2, so 2 root 3 is going to be the square root of 12, so we could write this as 2. M squared and k squared square rooted is just m times k, and then we have the square root of 3 here, divided by 4m squared. Obviously those m's will cancel, this one and this one, with the squared down there. And the 2's will cancel. If that becomes 3, that becomes 1, and that becomes 2, we end up with 2 plus or minus root 3 divided by 2 k upon m. And if you do those sums, we end up with 0.634 k upon m and 2.366 k upon m. So omega 1 0.796 k upon m. Omega 2 1.538 root k upon m. Yes.
3 plus minus root 3.
Yes, you're right. Sorry. Yeah. Apologies. Yeah. Just an oversight on my part. Yes, obviously 6 divided by 2 is 3. So that's the natural frequencies. To find the mode shapes, we go back up to this equation, okay? We divide both sides by x1. And so you end up with mode shapes. We end up with 2k minus m omega squared minus k 2k 2 minus m omega squared. Okay, so we've replaced x1 and x2 with 1 and r. And so for omega 1 is 0.796 k upon m square rooted. We've got 2k minus 2 times by 0.634 m times by k upon m. So that's this term times by 1 minus k r1 equals 0. So the m's cancel, We've got the k's, they cancel out with each other. We end up with 2 minus 1.268 minus R1 equals 0. Therefore R1 must be 0.732. So mode 1, which we write as big X with the 1 outside of the curly braces, is a vector 1 and 0.732. This is the convention I use for modes, okay? We've got big X, because it's a motion, inside curly braces, with the subscript outside representing the mode number, okay, mode 1. This is important for the next chapter when we talk about modal analysis, to know which modes we're talking about. Go through the process for omega 2. We've got 2k minus 2 times by 2.366 mk upon m minus k r2 equals 0. Again, the k's and the m's cancel out. And we end up with 2 minus 4.732 minus R2 equals 0. Therefore R2 equals minus 2.732. So the second mode shape, X 2 1 minus 2.732. Okay, so let's just run through the first part of the question. It said, find the equation of motion. Well, like I said, from this diagram, the quick method, we can go straight to the equation of motion, relatively in a straightforward fashion. The masses, the diagonal of the mass matrix are simply the masses added up with each other. Okay, the diagonals of the stiffness matrix are the springs connecting each mass to ground or to another mass. Okay, and the off diagonals are the minus the sum of the springs connecting the masses to each other. Okay. To find the natural frequencies, you need to find the mechanical impedance matrix first and then find the determinant of that. Well, we make the substitution. Okay, we know that the displacement is going to be an oscillation because the thing's oscillating. So you make those substitutions in here. We end up with this. Rearrange slightly, you get the mechanical impedance matrix. We're taking the determinant and setting it equal to 0. The determinant of a 2 by 2 is that times by this, minus that times by this. And so you end up with this equation. And then going through the algebra just to get our omega 1, 2 in the quadratic formula. 36 k squared m squared minus, this is going to be 4 times 2, which is 8, times by 3 is 24. So 36 minus 24 is 12. So it's root 12 m squared k squared. Obviously, you can simplify this down to 2 root 3. So we end up with 2 mk root 3. Obviously, the 6, 2, and 4, they all have 2 in common, so they can all be divided by 2. And m divided by m squared is 1 upon m. And so that can disappear as well. And we end up with 3 plus or minus root 3 upon 2 times by k upon m as our 2 natural frequencies. Okay? And then obviously you take the square root of those 2 terms and you get these 2 terms down here for omega 1 and omega 2. Then to find the mode shapes, we take our mechanical impedance matrix and then replace x1 and x2 with 1 and r. because we're assuming that x1 will move by 1 unit, whatever that is. Okay, meter, millimeter, inch, whatever you want to call it. One of those things, r will move by a relative amount. So we try omega 1, we stick that into here, we're omega, and I've decided for the sake of argument to use this equation times by that vector equaling 0. You could equally use this equation times by this vector and you get the same value for r. Okay, it's up to you how you want to do it. I've used the first one. Okay, so we end up with 2k minus 2m times by omega squared. Well, omega squared we know up here is 634k upon m. So I've got 6.634k upon m in there. M's cancel. And then we've got over here minus k r1. And the k's cancel because they're in every term equals 0. So we end up with 2 minus 1.268 minus r1 equals 0. So therefore r1 must be 0.732. So our first mode is 1 and 0.732. In the first mode, at this frequency, you excite at this frequency, if the mass 1 moves up by 1, mass 2 will move up by 0.732. Okay. Second natural frequency, 0.1538. Again, 0.1538 squared is 2.366, which you find on the previous up here. So we stick that in. M's and K's cancel. We end up finding R2 is minus 2.732. So in the second mode, at this frequency, okay, mass 1 will move up by 1, mass 2 moves down by 2.732, whatever.